So today we're going to talk about the microscopic view of current. And so we're going to look at what is really happening in a wire and then how it relates to how much current is actually flowing in a wire. And so when we look, if we were able to see the individual electrons in a wire, we would see that they are not moving in a straight line path at all. They are randomly moving, and kind of think of like a gas particles bouncing around randomly. And they are stopped by running into having collisions with atoms of the metal itself, and then other impurities that happen to be in that wire. So they're just bouncing randomly. But if we have an electric field, and you're going to get an electric field if you happen to take this wire and hook it up, let's say, to a battery, and that there would be an electric potential difference. We would have an electric field, and when we have an electric field, there is a force. And so now there's a force on these electrons that are bouncing around randomly, and they will move in a certain direction. Now, as you see in this picture here, which way they are moving, right, is of course towards the electric field. Remember, they swim upstream because the electric field is the direction a positive charge would move. And so we can see here that there is a movement in this picture to the left if it was electrons. Even when the electric field is applied, they do not move in a straight pattern, because again, every time in these little points, either the edge of the wire or they're hitting, there's collisions that happen. So they want to move in a certain direction. And in fact, when an electric field is applied, they begin to accelerate. But as they start to move faster and faster, you can imagine they hit more and more atoms, and therefore the resistance for their flow or velocity increases. And so at some point they reach a maximum velocity. And this velocity we call drift velocity. So there's some average velocity called drift velocity that is dependent, again, on how much force there is applied, and then how much resistance there is for those electrons to move through the wire. So we're going to now try to come up with some kind of formula for this drift velocity. What can we assume here, or how can we go about this? Well, the first thing is to think about what we have here. So we're going to make a section of this wire, all right? And I'm going to, so we have some kind of length of wire here. So I'm going to give that an L. There is a cross-sectional area here, A, that we could easily find out if we know the diameter of the wire. And let's first talk about what L would be. So we know that distance equals velocity times time. And this length, so I'm going to change my D to an L, would be equal to this drift. So if this was a bunch of electrons here that have a motion, then we would say that these electrons would travel this distance L if we knew the drift velocity, right, and some amount of time, okay? So in a certain amount of time, these electrons would drift through this length. And now this length, and we have an area, means that there is a volume. So we have really a volume of electrons here. And so we can come up with volume. Now we know volume is going to be area times that length. And now we can rewrite that and say then volume equals area, and since we have defined the length to be the drift velocity times that delta T. All right, so we're getting a little closer. So we know what kind of volume that we would have. And in this volume, we have some amount of electron density. So there's a certain amount of electrons that are in there. And so we are going to define that as well. So we are going to say that N is going to be equal to the electron density, all right? And that electron density, like any density, is always going to be per volume. So there is a certain number of electrons, right, in a volume. And normally then our unit for volume is going to be meters cubed, all right? Now, if we know that electron density, then we would also know then our charge. So Q, our total charge, would be equal to that electron density, so the number of electrons per volume, times the volume we know we have, times the charge on an electron. All right? So our total charge in this section is the electron density, so how many electrons there are per volume, times the volume. So then we have the number of electrons, and so then just the number of electrons times its charge would be Q. So now we're going to take this formula we have for volume and just plug it in here. So now we're going to know, right, that Q is going to equal the charge density times the area times the drift velocity times that time period which it occurs times the charge per electron. All right, now that's Q, but many times, of course, we are interested in current. So we want an current. So what do we know? Current, right, is the amount of charge that happens per time. And so we can say charge per time, right, would equal, we're going to take this, right? Can you imagine this being moved over to this side? So that would just be equal to N times A times VD times the charge of an electron. Now this equation has a special name. And this is known as the transport equation. See, that's a great name. All right, so let's label once again what we know here. So in this equation, so our current, right? So our current, right, in amps is equal to this charge density, which again is the number of electrons per meter cubed, times the cross-sectional area, which again, make sure you have converted it to meters cubed and not millimeters or centimeters cubed. Here is our drift velocity. And then this is just going to be the charge of an electron, right, in coulombs, and we know that. Sometimes in an easy problem, you'll be just given this charge density, but other times you have to actually calculate this charge density. So that's the next thing we're going to do, and that's almost the worst part of this because it involves a little bit of our chemistry knowledge. So let's go back to this volume here. So once again, right, we have some kind of a volume and it has a certain amount of electrons in it. So that's our electron density. So we can say again, so electron density is the electrons that we have, right, the number of electrons we have in our volume in our picture right here. But that density, it does not, remember, it's with density, it doesn't matter your sample size. So what if instead of having the volume of our wire with the number of electrons in our wire, we actually know something more if we had a different sample size? What if instead we viewed this as the number of electrons per mole, oh boy, if we knew the volume per mole. All right. So if we just did this for a different sample size, if we thought we had a mole of wire, then maybe we can get into finding this electron density a little bit easier. So let me scroll, and we're going to try to do that. Okay, so let me move this up. And let's see what we can do about this. So let me restate that here. So our electron density, we're going to do by knowing how many electrons there are per mole. And we can do that because we know the number of atoms per mole of any substance. And if we times that by the number of electrons per atom, right, then we would have electrons per mole. All right. And if we know the material that this is, we can do all of this. All right. And what would be here? What about this volume per mole? Well, our volume per mole, let's go off to the side here for a minute. We know that density equals mass divided by volume, right? So if I had the mass of a mole and the volume of a mole, right, then I could have the density. So I can switch this around, that the volume of a mole of any substance is equal to the mass of the mole divided by the density of that substance. So that's what I'm going to put now in the denominator here, because the volume of the mole there is going to be the mass of a mole over the density. All right, we're almost there. So let's again remember our chemistry. How many atoms are there per mole? Well, that's Avogadro's number, 6.022 times 10 to the 23rd. All right. The number of electrons per atom, I'm just going to leave this to electrons per atom, but sometimes in the problem it'll just say that there is one free electron per atom. Sometimes you have to work with it could have to do with the number of valence electrons that are available. All right. It should be specified in the problem, or you should be told somehow if all the valence electrons will be free, or if just one electron will be free per atom. All right. And then the denominator, what about mass of a mole? What do we know is the definition? The mass of a mole is considered to be the atomic mass. So as long as we have our periodic table, we're going to be golden. And then that's going to be over the density. So that is the density of the material, which normally is going to be a metal. So the density of the metal that the wire is made out of. So the atomic mass divided by the density will give you the volume of a mole. This is the number of atoms that are in a mole, and then times it again by the number of electrons will give you this density. And so many times, if you are going to be using this transport equation, you have to do an aside. You can't just do N times A times VD times E. You have to first stop and use this formula down here to discover the charge density. So this charge density can be like 10 to the 28 or 10 to the 29 charge per meter cubed. All right, so we can get some crazy numbers coming out of this equation.